Hello guys, welcome to Ramta Solutions. Today in your differentiation calculus, we are going to look at concavity. So at the end of this video, you must know how to draw these graphs or how to define them. Okay, you will know also the meaning to these graphs that you are seeing on the page. All right, so without any waste of time, let's get into it. So, one, we are going to introduce to basically define what is concavity, and then we are going to use an example where we are going to investigate this concavity and finally summarize the details of that investigation or summarize the results of that investigation. Okay. So without any waste of time, let's get into it. So when we talk of concavity or what concavity does, basically it indicates whether gradient, it indicates whether gradient increases, decreases, or remains the same. Okay? Whether gradient increases, decreases, or is stationary. To remain the same is to say it is stationary. Okay? Right. So now what we are going to do, we are going to use an example of this cubic graph or cubic function that we used in the previous video. F of x equals x cubed minus 6x squared plus 9x. Okay, so we are going to study this graph. As you can see, when we're looking at this graph, we know that A is positive, so the graph will be ending with a smiling face. But because these are the contents that we have from the previous video, we do recall that it was something like this. Right, it was something like this. Right, it was something like this. Let's say it touches here. So this was 0, this was 3, this was 1 and 4, and there was a point of inflection at 2 and 2. Let me say this is 3 and 0, and this is 0 and 0. Right? So this is what the cubic graph looked like. Right, this is what the cubic graph looked like. So we say concavity indicates whether gradient increases, decreases, or is stationary. Okay, so we are going to basically find the first and second derivatives of this function. Okay, so let's get into it. So we are basically continuing, or we are basically pagati inside the investigation. Okay, 6x squared plus 9x. First derivative would be f of x equals, or maybe let me not even write it here. I'm just gonna copy that. That graph. Let me copy the graph. Let me copy the graph and save time. Okay, let me just copy the graph. Oh boy, what am I doing? Yeah, let me just copy the graph. Yep. Okay. Cut. Where is it? Cut. And then I'm going to paste it into this page. Let me see. Here is it. Perfect. So now we can see. Now let's begin. We will say we had f of x. All right. We had f of x equals x cubed minus 6x squared plus 9x. And then f prime of x would be 3x squared minus 12x plus 9, f double prime of x would be 6x minus 12. Okay, so we are going to be investigating this, and here we will be writing our x values. The x values that we see here, we see 0. Let me try 1, or maybe I have moved this 0 too far. 0, 1, 2, 3. I think that's enough. 0, 1, 2, 3. Okay. Now, okay, so when you look at this f of x, this is f of x, right? When you look at it, x values that are less than 0 are negative. They have a corresponding y value that's negative. So let's not waste time and say this is negative. Here it's 0, and above 0 but less than 1, the corresponding y values are positive, so I'm not going to waste time. Even at this point, it's positive, 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 positive. At 3, y value is 0. Greater than 3, y values are still 0. Alright? Greater than 3, y values are still greater than 0, meaning positive. Alright? Okay. So when you okay, we are sorted, so we can now move on. Now, this is the first derivative. We said the first derivative is the gradient, right? So let's see. Think of a number that is less than 0. I will say, for example, let me put that number. I'm going to put -1. Here, I'm going to put number that is greater than 0 but less than 1, maybe 1.5. Here, maybe let me try 2.5. Here, maybe let me try, 1.5, not 2.5. So this is 0.5, 1.5 maybe. Here, maybe let me try 2.5, and here any number I will try 5. Okay, so think of any number greater than 0. If you substitute that number into this expression, you will get a negative, right? However, with this one, it's easy. We can see from this equation, from this graph, so we can just move on. So let's substitute this -1 into f prime x. Let's do it. Let's take out our calculators. So this is 3 into -1, close the bracket, squared, minus 12, open bracket, minus 1, squared. Not squared, minus 1, and close your bracket, plus 9. We find a positive, right? We find a positive. Now, when we put 0, when we're done with negative, now when x is 0, if we put 0, what do we get? We get 3 into 0, it's a positive. Now let's try 0.5. When we try 0.5, let me see. I will try 0.5. Where there's x, we now put 0.5. I think we will still get a positive, right? Yes, it's still a positive 3.75. Here is it. Now, let's then, maybe let me change the colors so I can be consistent. Yeah, let me just change the colors. Now, when x is 1, we get what? When x is 1, we get 0, right? We get 0. I want you to check it out. I will confirm where x is 1, we get 0. Yeah, we get 0. Yep. Now, when x is greater than 1 but less than 2, meaning a number that is greater than 1 but less than 2, we said, for example, 1.5, we will get a negative. Even at 2, we will get a negative. 2.5, a negative. At 3, let's see. Where there's x, we put 3. So this is 0. All right, this is 0. Right? Okay. Now, at this point, when x is 3, f prime x is 0. Okay, perfect. Now, we're now thinking of a number greater than 4. Greater than 3. We said we will take 5, for example. When you substitute in place of x, you put 5, you are going to get a positive value. So we can still say it's positive. Okay, perfect. Cool. Now, let's then substitute these very same values into f double prime x. Let's see, when x is -1, 6 times -1 is -6 minus 12, it's a negative. 0 times 6 minus 12, it's negative. 0,5, it's still a negative. 1, it's still a negative. When it's 1.5, it's still a negative. When it's 2, we get a 0. When it's 2, we get a 0. Okay. When it's 2.5 is greater than 2, we get a positive. When it's 3, we still get a positive. So it's still positive y. Right? So, okay, this is how we this is how we investigate in concavity, but we haven't yet discussed the results, right? We haven't yet discussed the results, right? We haven't yet discussed the results. The important results for me are these. I want you to see for the first derivative, I want you to see that we're saying where there is a stationary point, I'm going to write SP. Okay, I'm going to write SP. Where there's a stationary point, can you see that our derivative is 0? Where when you substitute the x value of the stationary point, our derivative is 0. What does it mean? We said the first derivative is the gradient, right? So x value of the stationary point, when we substitute it into the first derivative, the value is 0. Now I want you to pay attention to this. When you look at this, you can see that, okay, we are basically seeing, if you take this, I'm going to copy it into the new page. It's important. Okay? Oh no, maybe let me not copy it. I'm just going to explain it from here. As you can see here, we're saying the gradient increases, gets to 0. So I'm going to show you what I mean. Gradient increases, gets to 0, decreases. Can you see that? Positive gradient means gradient increases, gets to 0, decreases, negative. Now from here, we said its gradient is negative. So this means gradient decreases, it gets to 0, and increases. Can you see? This is how your graph looks like. Can you guys see that? This is how your graph looks like. Look at it here. Can you see it? This is how your graph looks like. Okay, this is how your graph looks like. But then it doesn't end here. Okay, it doesn't end here. I have included second derivative. The second derivative somehow will help you determine whether your point is concave up or concave down. And please note, this one here is concave down, which we call local maximum. This one here is concave up, which we call local minimum. Okay? So I want you to see something. Now I'm going to take stationary point and point of inflection. So this one here is the point of inflection. All right, let me just call it PI. It's the point of inflection. Point of inflection, its x value is 2. I want you to see something. If we use the second derivative, it says to us, if a stationary point is a maximum, that x value, when we substitute it into the second derivative, it will be negative. Can you see that? It is negative, negative, negative. Now, again, if your stationary point is a minimum, when you substitute the x value of that stationary point into your second derivative, the value of the second derivative will be positive. This is when it is a minimum. Again, if you substitute a value into your second derivative and you get 0, that point is a point of inflection. Can you see that? It's a point of inflection. Now the summary of our notes are like this. we have, this one is called local mean, this one is called local max, this one is called point of inflection. It's like this or it's like this. Okay, so we call this one local minimum, we call this one local max, and we call this one here point of inflection, right? We call this one here point of inflection. With this one here, it's concave up, all right? This one here, it's concave down. This one, it has no concavity. Gradient doesn't change here. Okay, so gradient doesn't change. I don't even have to mention it. Gradient doesn't change. Okay, gradient doesn't change for point of inflection. Remember, it's one or the other. Okay, so let me just show you. It's one or the other. Maybe let me space it a bit. It can be this or it can be this. Okay, so with this one, let's go back. When it's concave up for local minimum, as you can see, if you were to put 3, in place of x you put 3, you will get a positive value on the second derivative. In other words, I mean f prime of x is greater than 0 for a local minimum. So if your stationary points, when you substitute them, the x value of your stationary point, when you substitute it into your second derivative, you get a positive value. That point is a minimum. It is smiling. So if that point, when you substitute it into your second derivative equation, you get a negative. It is a maximum. It is frowning. So basically we're saying second derivative of x is less than 0 when it is a local max. Okay, when it is a maximum value. Okay, finally, if when you substitute your stationary point, you realize that your point of inflection, your second derivative equals 0, you will then realize that this means you have a point of inflection. At point of inflection, second derivative is equal to 0. Okay, remember, at point of inflection, second derivative is equal to 0. Okay, so these are the explanations that we get, or this is the summary that we get from this investigation. Okay, from this investigation. Remember, the equation of the first derivative will basically give you the concavity. It will show you that, so when I look at this one, especially in this example, it says when I move from the left to the right, I'm getting my gradient is increasing. When it gets to x equals 1, it becomes 0. It then decreases. As you can see, it then decreases, gets to 0 again, and then changes direction, increases. As you can see, it's increase, decrease, or decrease, increase, depending on your value of a. Okay, depending on your value of a. So this is very important for optimization. If you can know this, when you're optimizing, you will be okay for optimization. Okay. To those that are using American English, I'm sorry, I'm not writing that. So this is good for optimization. Okay, so this is good for optimization. You are going to use these for your optimization. Okay, for your optimization, you're going to use this. All right, guys. So this is the summary that you needed for this particular question, or this is the summary that you needed for this aspect of concavity. All right, so I hope you will ace your exams. So see you next time, and salang sintle.